The COVID-19 pandemic took the world by surprise. Globally, everything has stopped. Projects have been delayed, workplaces closed, and schools shut down. However, students should continue their education to different modes of teaching and learning. Particularly in our university, we are offering a flexible learning arrangement. Some are synchronous and synchronous. Some synchronous components are the online class through Zoom or Google Meet or WebEx, and some are using instant messaging. And for the asynchronous component, some faculty members are required or the faculty members are required to create modules or the learning guide for the students. Some are creating handouts, chatting, and other electronic computer-based instruction, such as the Google Classroom. But the very challenging one of those different learning materials is to create video clips. But then, this different model or this model, the flexible learning arrangement, is currently the best alternative, as keeping schools open possess a safety risk for students. But not everyone has computers. Not everyone has the technology. Not everyone has the internet. The decision to close schools forced the teachers to change from analog to digital teaching methods from one day to another. And that was exactly what I did. Immediately, I took responsibility to provide a quality education to my students. Our responsibility as teachers do not cease even if schools close. We need to adapt the new reality in no time. Leadership, professionalism, cooperation at school are very important. Some of us are sharing digital teaching experiences, learning methods, and recommendations on digital platforms. Once again, welcome to Double Z TV, the virtual classroom for mathematics and the modern world. Good day, everyone. So this will be our topic for today. So this is all about mathematical language and symbols, the chapter 2, or the language of mathematics. So the aim of this chapter is to introduce to you a mathematical way of thinking that can serve you in a wide variety of situations. Often, when you start work on a mathematical problem, you may have only a vague sense of how to proceed. You maybe begin by looking at examples, drawing pictures, playing around with notation, rereading the problem to focus on more of its details, and so forth. The closer you get to a solution, however, the more your thinking has to crystallize, and the more you need to understand, the more you need language that express mathematical ideas clearly, precisely, and ambiguously. This chapter will introduce to you some of the special language that is foundation for much mathematical thought. The language of expressions, sets, relations, functions, and binary operations. Just think of the chapter like the exercises you would do before an important sporting event. So its goal is to warm up your mental muscles so that you can do your best. So basically, this will be our guide for the very basic knowledge that we need to understand to better cope up with this mathematics in the modern world subject. So the very important concepts that we need to understand. So hopefully you will get more knowledge under this our discussion. So to start with, these are the topic outline for Chapter 2. First one is the characteristics of mathematical language, the expression versus sentences. Then we have the conventions in the mathematical language, the four basic concepts, that's what I've said earlier, elementary logic, and formality. So, at the end of this chapter, these are the learning competencies or the outcomes, knowledge or skills expected from every student to be developed and mastered. One is to discuss the language, symbols, and conventions of mathematics, explain the nature of mathematics as a language, acknowledge that mathematics is a useful language, compare and contrast expression and sentences, identify and discuss the four basic concepts in mathematical language, to list and discuss some basic operations on logic and logical formalities, perform operations on mathematical expression correctly, to articulate the importance of mathematics in one's life, and to express appreciation for mathematics as a human endeavor. So start our topic. So we have the characteristics of mathematical language. So for 1,000 years, mathematics have developed spoken and written natural languages that are highly effective for expressing mathematical language. So this mathematical language has developed and provides a highly efficient and powerful tool for mathematical expression, exploration, reconstruction after exploration, and communication. So its powers comes from simultaneously being precise and yet concise. But some of mathematical language is being used poorly because of poor understanding of the language. So notably, mathematics has its own language, much of which we're already familiar with. For example, the digits. We have the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when we say 0 or nothing, so we understand its meaning. So there are many symbols in mathematics, and most are used as a precise form or shorthand. It is quite important that we familiar ourselves using the symbols. And we should need to understand its meaning. So the Greek alphabet, some of those have different meaning in mathematics. Like the P in Fibonacci, that is equivalent to 1.61 blah blah blah. We have the pi, which is equivalent to 3.14, and so on. So all of those have their own meaning in our mathematical language. So mathematical language can easily be understood by context and convention. So context is what we are working or the particular topics being studied, while convention is where mathematics and scientists have decided that particular symbols will have a particular meaning. So, for example, this symbol stands for dollars, and this is the specific meaning of this symbol. This one stands for percent. So, those are some of the symbols that have a particular meaning in mathematical language. Now, let's define formally what is mathematical language. So, mathematical language is a system used to communicate mathematical ideas. It consists of some natural language using technical terms, or the mathematical terms, and grammatical conventions that are common to mathematical discourse, supplemented by a highly specialized symbolic notation for mathematical formulas. So one of the characteristics of mathematical language is that mathematical notation is used for formulas, has its own grammar and shared by mathematicians anywhere in the globe. So we are sharing the same grammar anywhere in the globe. So when we say 2 plus 5, the answer is 7. So, any other countries, 2 plus 5 is also 7. So, our own grammar here are the same with the other country. So, that is what we call the mathematical language. Has its own grammar shared by all the mathematicians around the globe. So, mathematical language is being precise, concise, and powerful. So, what do we mean by precise? Mathematical language as being precise. So, the characteristics of mathematical language being precision in mathematics is like a culture of being correct at all time. So, when we say precise, we should be correct at all time. Mathematical culture of precision has developed a precise, highly symbolic language and dialect manner that allows for the adoption, adjustment, and cumulative refinement of concepts based on experiences, and mathematical reasoning is expected to be correct. So first, mathematical language is being precise. Second, mathematical language is being concise. So, mathematical language must be concise or show simplicity. Being concise is a strong part of the culture in mathematical language. So, it's very important in mathematics. Very concise. Short lang in very short way we can understand. And we also note that that is precise. So, in expressing your language using mathematics, you can express it in a short way, but then it is precise. And lastly, mathematical language is being powerful. So mathematics language must be also powerful. It is a way of expressing complex thoughts with a relative ease. The abstraction in mathematics is the desire to unify diverse instances under a single conceptual framework and allows easier penetration of the subject and the development of more powerful methods. According to Galileo Galilei, mathematics is the language in which God has written the universe. It can be attributed that mathematics is a universal language because the principle and foundations of mathematics are the same everywhere around the world. When we say 5 plus 5 equals 10, if we write it as an Arabic numeral, the concept of 10 items is the same anywhere in the world. So that is one of the very important characteristics of the mathematical language. Okay, so that's it for our first topic, the characteristics of mathematical language. Now, let's proceed with our next topic. This is all about the expression versus sentences. So what do we mean by expression? So when we say expression or a mathematical expression, so it is a finite combination of symbols that is well defined according to rules that depend on the context. Symbols can designate numbers, variables, operations, functions, brackets, punctuations, and groupings to help determine the order of operations and other aspects of mathematical syntax. So when we say expression, correct arrangement of mathematical symbols to represent the object of interest. It does not contain a complete thought. Take note. Expression does not contain a complete thought, and therefore, it cannot be determined if it is true or if it is false. So we cannot determine if the given is true or false. That is an example of expression. For example, we have greater than. So greater than is an expression, but then you cannot determine if that is true or false. We have the addition. We can also have a combination of symbols. We have 2 plus 3. But 2 plus 3 is an expression. Why? Because we cannot determine if that is true or false. Also a combination of a symbol and a variable. So we have, for example, let's say 2x. So 2x is an expression, but we cannot determine if that is true or false. Now, what is all about expression. So some types of expression are numbers, sets, and functions. Okay? So those are expressions. Digits are expressions, sets are expressions, and functions. Now, what is the difference? But now is a sentence. When we say sentence or mathematical sentence, it is a statement about two expressions, either using numbers, variables, or a combination of both. So this time, we are using symbols or words like equals. So we're using now equals, greater than, or less than. So this time, we're now comparing the two expressions. So in other words, it is correct arrangement of mathematical symbols that states a complete thought. Yan. So since it states a complete thought, then it can be determined whether it is true, it is false, sometimes true, or sometimes false. For example, we have, say, 2x plus 3 equals 6. 4x equals 1. So, is this true or not? So, this is an example of sentence. If I will substitute the value of x in this equation, or in this expression, then we have 2 times 1 plus 3 equals 5. So, therefore, this particular sentence is false. Because 2x plus 3, if x is 1, is not equals to 6. So that is what we call now a sentence. Another one, 1 plus 2 equals 3. So 1 plus 2 equals 3 is true. So this is an example of a sentence where using this symbol equal sign. Or we can have 2 is greater than 5. So 2 is greater than 5 is also a sentence. But 2 is greater than 5 is false. Because 2 is less than 5. So I'm using the symbol less than. You can have 10 is, I'm using the word greater than. So let's say have 10 is less than 12. So this statement is true. So those are the difference between an expression and a sentence. So I hope you understand the basic definition of the two. Okay, so that's it for our topic 2.2. Now, let's proceed with topic 2.3, the conventions and mathematical language. So, mathematical language have conventions and it helps individual distinguish between different types of mathematical expression. So, what is now mathematical convention? So, when you say mathematical convention, so it is a fact, name, notation, or usage which is generally agreed upon by mathematicians. So, let's say, for example, one evaluates multiplication before addition, following the principle of PEMDAS, which is the parentheses, exponent, multiplication, division, addition, and subtraction. So mathematicians abide by conventions to be able to understand what they write without constantly having to redefine basic terms. So almost all mathematician names and symbols are conventional. So that's very important. So like any other discipline, mathematics also has its own brand of technical terms. So within mathematics only, we are defining terms which is very technical, which is only in mathematics. But when it comes to other subjects, they have their own meaning. So in some cases, a word in general usage has a different and specific meaning within mathematics. Some examples are, say, group. So in general usage, group is a group of person, a group of objects, or a group of anything you want to define. But in mathematics, a group is not a group of person, not a group of object. So it has its own characteristics. There are different properties you need to provide to know if a given expression or sentence is a group or not. Same with ring, field. Those different characteristics in mathematics that you need to define first, or you need to find first to be able to determine if that is a group, a ring, or field. So term, so in mathematics, we're familiar with this. These are a combination of a symbol and a variable, or a symbol or a variable alone. So those are terms. So we can have 2 terms, 3 terms by using some of the operations in mathematics. So factor, in general usage, when you say factor, what are the factors to being a very good man, a very good woman? What are the factors to be a success in your life? So that is in our general usage. But in mathematics, when we say factor, these are there are some formulas, different formulas in factoring, okay, specifically in algebra. So those are some of the terms that in mathematics they have their own specific meaning, and it is acceptable worldwide. Also, in other cases, there are special terms have been introduced. Some of them are tensor, fractal, and punctor. And there's a lot of special terms in mathematics. So mathematical statements also have its own taxonomy, like axiom, conjecture, theorems, lemma, and corollaries. These are also some mathematical phrases or mathematical jargon used with specific meanings, such as, so we have if and only if, necessary and sufficient, and without loss of generality. So we all know that formulas are written predominantly from left to right, even when the writing system of the substrate language is right to left. So parang when you're writing from right to left, parang hirap naman nun if you're writing the formula from right to left. So we all know that in writing the formula, that is from left to right. So Latin alphabet is commonly used for simple variables and parameters, or the Greek alphabet that is usually used for our some parameters in mathematical language. So these are some of the mathematical expressions that you may encounter in the preceding topic. So we have the equal sign, the addition, subtraction, multiplication, division, greater than, less than, element. So this will be under the sets for all. To define the sets, there exist, implies, if and only if, approximately, then we have this, therefore, and infinity. And there's a lot some mathematical expressions that you may encounter. We have less than, or we have the greater than or equal to, the less than or equal to, and so on, and etc. So there's a lot of mathematical expressions that we are using and accepted worldwide. Next, we have Unit 2.4, the four basic concepts that we need to understand in mathematical language and symbols. So language serves as a tool for teaching mathematical concepts. It can show how to make syntax and structure of mathematical language clear and explicit to understand the fundamental mathematical concepts. Language also serves as a major pedagogical tool to understand how, what, and why things are said. We need to be familiarized with the 4 basic concepts and mathematics before moving up to more complicated mathematical structures. So these are the 4 basic concepts that you need to be familiarized with. First is the language of sets. Second, the language of relation. Third, the language of function. And finally, the language of binary operations. So let's start with the language of sets. So what is set theory? So set theory is the branch of mathematics that studies sets or the mathematical science of the infinite. George Cantor, who is a German mathematician, he is considered as the founder of set theory as a mathematical discipline. So let's define a set. So a set is a well-defined collection of objects. So when we say well-defined, it should be complete, defined, completely defined. So the objects are called the elements or the members of the set. So this is the notation for the element of the set, while the symbol stands for not an element of the set. So let's have these following examples of sets. So first one, we have set A equals the set of all x such that x is a positive integer less than 10. So this is well defined because we can list all the elements which are positive integer less than 10. Name to name, we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So another example, we have set B equals the set of all x such that x is a real number. So by the way, in sets, it's very important that you're familiar with some terms or symbols that we'll be using. If you have a symbol Z, this stands for an integer. And R stands for a real number. So this is just a review. So x is a real number, so if we will compute this equation, so we'll get x is equals to positive and negative 1. So those are the elements of set B. Another example, we have set C equals the set of all x such that x is a letter in the word set. So obviously the elements are S, E, and P. Another one. So set of all x such that x is an integer and x is greater than 1 but less than 8. So this time, so D is equal to 2, 3, 4, 5, 6, and 7. So 2, 3, 4, 5, 6, 7 are elements of set D. So it is greater than 1 but less than 8. Okay, and another final example for sets. So we have a set of all x such that x is a set of vowel letters. So set of vowel letters in our alphabet are A, E, I, O, U. And these are the elements of set A. So take note that those examples are example of set. It means it followed the definition, which is a well-defined collection. Because if that given example is not well-defined, then we cannot determine what are those members or what are those elements of the given set. So I hope it's very clear to you the basic concept or the basic definition of the set. So let's try some of the problems. So you just indicate whether the following define a set. So let's have the list of program offerings of CBC Bacoor City Campus. So is this a set or not a set? So obviously, we can list the program offerings of CBC Bacoor Campus. We have the CS, IT, HRM, or HM, BM, Education, Criminology, Psychology. So therefore, this is an example of the set. Let's have another example. The new elected district councilors of City of Bacoor. So, yes, we can get these listings in the City Government of Bacoor page. And this is an example also which define the set. This one, the collection of intelligent crocodile in Manila Zoo. So is this a set or not a set? Obviously, how can we define or what are the basis of an intelligent crocodile? So in this case, this is a vague definition, or one can define that crocodile is intelligent but the other one cannot define if that crocodile is intelligent based dun sa nakikita. So in this case, this example of sentence is not well defined. So therefore, since this is not well defined and we cannot determine or how we define intelligent crocodile, this example is an example of not a set. Okay, so let's have some more examples of the set. So list the elements of the set. So set A equals a set of all x such that x is a letter in the word mathematics. So in this example, the answer is MATHEICS. So take note in this case, in the word mathematics, so M appeared 2 times, T also appeared 2 times, but in this case, you will only write 1 because if M is already a member, so you don't need to put another M because it's already part of, or it's already a member of that element. So you need to only put once. So M and T will be right only as 1. So take note of that. So therefore, the set A is equals to MATHEICS. Same also with letter A. So letter A appeared twice. So you only need to write once. Okay? So that's it. Another example. So we have the set of all x such that x is a positive integer, wherein x is greater than or equal to 3 but less than or equal to 8. So this time, this symbol is very important. Greater than this one, x is greater than or equal to 3 and x is less than or equal to 8. So this time, we have the symbol equal sign. So therefore, 3 and 8 is part of, or 3 and 8 is also a member of set B. So the final answer will be 3, 4, 5, 6, 7, and 8. Another example. So this example is a infinite set. So how we compute or how we list the elements of an infinite set, that will later on discuss the definition. So a set C is a set of all x such that x is equal to 2n plus 3. So this time we have this equation 2n plus 3 where n is a positive integer. So in this case, first thing to do is to determine the values of n, because we need to substitute the values of n in these equations so that we can get the listing of all the members of set C. So in particular, since n is a positive integer, then our n starts with 1, 2, 3, 4, 5, and so on. So this is again, what I've said, an example of infinite set that I will discuss later, the formal definition. So for n equals 1, substituting the equation 2n plus 3 is equals to 2 times 1 plus 3 will give 5, and 5 will be our x sub 1. The first x, or the first member of our set C. Second, for n equals 2, then we have 2 times 2 plus 3, then we have 7. For n equals 3, then we have 2 times 3 plus 3, then we have 9. If n is 4, then we have 2 times 4 is 8 plus 3 equals 11. And finally, if n is 5, then we have 2 times 5 plus 3 equals 13. For this example, since this is an infinite set, so you don't need to compute 5 computations. You can compute only at least 3. So at least 3 computations, it suffices now your answer. So 7 will be your x sub 2. This will be 9 is our x sub 3. Then 11 is our x sub 4. Then 13 is our x sub 5. And therefore, the elements of C are the members x sub 1, comma, x sub 2, comma, x sub 3, comma, dot, dot, dot. So, these are the elements of set C. So, therefore, the answer is we have 5, 7, 9, 11, 13, and so on. So, as what I've said, you can answer in this way. So, C, you can only compute the first 3 term, which is 5, 7, 9, comma, dot, 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 or this ellipsis. So, this one stands for infinite terms. Okay? So, that is how to list the set if the given example is an infinite set. Okay, that's it. So there are 2 methods of writing sets, either by raster method or by rule method. So let's define first what is a raster method. So the elements of the set are enumerated and separated by a comma, and it is also called tabulation method. So usually in writing the set, so this is enclosed with a bracket. So we have set A with an elements 1, 2, 3, 4, and 5. So this is how to write the set using raster method. Another method is using the rule method. This time, this is descriptive phrase. So this is used to describe the elements or members of the set, and it is also called the set builder notation. So usually the symbol used is written as in this way: a set of all x such that your description of that given set. So for example, if we have this one, a set A with elements 1, 2, 3, 4, 5, so using the rule method, so this will be the description: a set of all x such that x is a positive integer less than 6. So for this example, in writing the rule method, so there's different way on how to answer or how you describe the elements. So you can have other answer except this one. Okay? So let's have this one. Let's try A equals 1, 2, 3, 4, 5, and I will show you some of the other answers using the rule method. X is the first first 5 counting. numbers. So that is one way how to answer that given expression or given set. Another one, we can also write A is equals to the set of all x such that x is an element of an integer and x is greater than or equal to 1 but less than or equal to 5. This is another way of writing the rule method using this example. So in other words, in writing the descriptive phrase, it's up to you on how to describe the elements of the members of the set, but don't forget that it should be well defined. So that's it. Let's have some of other examples. So write the following sets in roster form. Okay, so X is the letter of the word modern. So from the word modern, then we have M-O-D-E-R-N. So since no letters are repeated, so therefore, this is the answer. So this is a roster form. So this is enclosed with a parenthesis separated by a comma. So that is answer for example 2.2a. Another one, this one. A set of all x such that x is greater than 3 but less than 8. And x is an element of integer. So this is very important, the other definition, because if just an x is greater than 8, greater than 3 and less than 8, we have 7.9, 7.8, 7.99, 6.9, 6.8. So in that case, we cannot determine the members or the members of that set. So it should be well defined. So this one is very important. This means that I'm asking only for the element of an integer. So since it is an integer, so the answer is, so we have B is equals to 4, 5, 6, and 7. So hindi po kasama yung 8 since less than 8 siya. Hindi rin kasama yung 3 since greater than 3 yung ating given set. So the final answer is 4, 5, 6, and 7. Let's have another example. So a set of all x such that x is the set of zodiac signs. In this case, we will just list all the zodiac signs. So we don't need to write everything. We can write in this way because it's a common that since we are writing this that it means there are other 6 zodiac signs na pwede po nating isulat. So this is an example of writing the set using a roster form. Okay, now let's have another example. This time, write the following sets using the rule method. Nara, mahogany, mulabe. So these are 3. So when we say a set of 3, so kung 3 lang ang sabihin natin or 3, so madaming 3. So ano po kaya yung mga kasama nito? So these are an example of a set of non-bearing trees. So as you can see, we have Nara, mahogany, mulabe. So these are the set of non-bearing trees, yung wala pong bunga at hindi po natin siya makakain. Okay? Another example. We have the DOJ, DOST, DOH, DSWD, DNR, CHEDEP, ED, etc. So, I hope you're familiar with this one. So, these are the government agencies or a set of government agencies. So, in particular in our country. So, to make it clear, we can put it a set of government agencies in the country. So obviously, these are the different agencies under the umbrella of our president, or under the government agency. Another one, we have botany, biology, chemistry, and physics in dot dot dot. So obviously, these are branch of science or science subjects. So this is a set of science subjects. So botany, biology, chemistry, physics, and so on. So that is how to write a rule method in sets. Okay, so I hope you understand the difference or the methods of writing the sets, the rooster method, and the rule method. Okay, so let's define some terms on sets. That is very important. So what are the different terms? In particular, we have the finite and the infinite sets. We have the unit set. We have the empty set, the universal set, and the cardinality. So those are 5 terms or some terms involving sets. So let's have first the finite set. So when we say finite set, it is a set whose elements are limited or countable, and the last element can be identified. So in our previous example earlier, some of those are finite set. So in that case, we can count how many elements are there or how many members in the given set. So for example, so set A is a set of all x such that x is a positive integer less than 10. That is our first example earlier. So in this case, so for letter A, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can count how many possible members are there in set A. Another example, we have set C, we have SET, so there are 3 members. So we can count. So we have this set E is A, E, I, O, U, so there are 5 elements. So that is an example of a finite set. So those elements are countable and we can identify what is the last element of the given set. Okay, next is infinite set. So when we say infinite set, this is a set whose elements are unlimited or countable, and the last element cannot be specified. So for example, if we have the set F, which is equivalent to dot dot dot, -2, -1, 0, 1, 2, dot dot dot, then this is an example of infinite set. So we cannot count how many members belong to a given set. And take note that this is equivalent to set of integers. So this is a set of integers. Set of integers. Next, we have G is equal to set of all x such that x is a set of whole numbers. So this time, this is using the rule method. Yung letter A is using the roster method. So this time, this is also an infinite set because a set of whole numbers, we don't know what is the last element. We cannot specify the last element. So for the set, we can start. So we have 0, 1, 2, and so on. So we can list some, but then we cannot list everything because it's unlimited. So therefore, this is uncountable, and this is an example of infinite set. Last one, we have this one, a set of all X such that X is a set of molecules on the Earth. So we can name a few, but we cannot name everything or every molecules on Earth. So this is an example of infinite set. Okay, next we have the unit set. So a unit set is a set with only one element. So it is also called singleton. So it means the set is only one element on it. For example, we have the set I, a set of all X, which is X is a whole number, greater than 1 but less than 3. So in this case, I equals 2 or I. So the element of set I is 2, which has only one element. So this is what we call an example of a unit set. So obviously, the next example is an example of a unit set. And the third example also. Now, we have the empty set. So when we say empty set, it is a unique set with no elements. This is usually also known as null set. So it is denoted by this symbol or this symbol, a bracket with no element. So for example, L is a set of all X such that X is an integer less than 2 but greater than 1. So is there an integer which is less than 2 but greater than 1? So I think there's no such integer exist, because after 1 we have 2. So there is no integer exist which is less than 2 but greater than 1. So in this case, L is empty. So therefore, there is no such integer exist which is greater than 1 but less than 2. Therefore, this is an example of an empty set. Another example is that a set of M, set M equals set of all X such that X is the number of panda bear in Manila Zoo. And we all know that there's no panda bear in Manila Zoo. So that is why set M is empty. So there's no panda bear in Manila Zoo, so set M is empty. So therefore, this is an example of empty set. Another example is the set of all X such that X is the set of positive integers less than 0. So there's no such integer or there's no such positive integers which is less than 0, because all positive integers are greater than 0. Therefore, set N is also empty set. So that is empty set. Okay, next is universal set. So when you say universal set, all sets under investigation and any application of set theory are assumed to be contained in some large fixed set called the universal set, and is denoted by the symbol U. So this symbol is used. So for example, so we have U is equal to the set of all X such that X is a positive integer. X squared equals 4. So in this case, the value of U is, so the value of the elements of U is 2. There's only one element. So in this particular example, this is also an example of a singleton or a unit set. So we have U is equal to 1, 2, 3, 4, 5, 6, 7 until 100. Or U, the set of all X such that X is an animal in Manila Zoo. So if you list all the animals in Manila Zoo, then that's an example also of a universal set. So when we say cardinality, so the cardinality number of a set is the number of elements or members in the set. The cardinality of set A is denoted by this symbol. So let's have an example. Determine the cardinality of the following sets. So given set E, we have A, E, I, O, U. So in this case, we have 1, 2, 3, 4, 5. So just count the number of elements in the given set. Therefore, the cardinality of set E is 5. Another example, we have set A is equal to set of all x such that x is a positive integer less than 10. So in this case, so we have n A equals 9 because the set of positive integer less than 10 are 1, 2, 3, 4, 5, 6, 7, 8, 9. So therefore, there are 9 elements in set A. So the cardinality of set A is 9. So it's very easy how to determine the cardinality of a number. So in other words, the cardinality of a number is just count the number of elements in a given set. So in particular, this is usually you can get the cardinality of the number if that given set is finite set. Because if the given set is infinite, then we cannot count the elements of those sets. So another one, we have set C with an element SET. So obviously, the cardinality of set C is equivalent to 3. Okay, so those are some of the terms involving sets. Okay, now we have the Venn diagram. So what is a Venn diagram? So Venn diagram is a pictorial presentation of relation and operations in set. So also known set diagrams, it show all hypothetically possible logical relationship between finite collection of sets. So Venn diagram was introduced by John Venn in his paper on the diagrammatic and mechanical representations of proportions and reasonings. So he constructed with a collection of simple closed curves drawn in the plane of normally comprised of overlapping circles. So the interior of the circle symbolically represent the elements or members of the set, while the exterior represent the elements which are not the members of the set. Okay, so what are the kinds of sets? So we have the subset, the proper subset, the equal set, and we have the power set. So let's define first what is a subset. So if A and B are sets, A is called subset of B if and only if every element of A is also an element of B. So symbolically, this is read as set A is a subset of set B if and only if for all. So as what I've said earlier in our symbols, this stands for all. For all X, X is an element of set A implies that X is an element of B. In other words, A is a subset of B if X is an element of A, then that is also an element of B. Okay, let's have an example to understand the subset. Given this example, we have set A, we have CDE. CDE, so this will be our set A. Then set B, we have ABCDE. This one, the big circle. So as you can see, this small circle which is inside the big circle. So obviously, set A is a subset of B because we have elements CDE, which is an element of set A, is also an element of set B. We have C, D, E. So in this case, set A, therefore, set A is a subset of set B. Since all elements of A are also in set B. So that is an example of subset. So in case that there is, for example, if I will add, let's say, F here in our set A, therefore A is not a subset. So in this case, A is not a subset of set B. Why? Because F is not an element of set B. So as simple as that. That is how how we understand the subset. Okay? Another one, we have the proper subset. So let A and B be sets. A is a proper subset of B if and only if this one, if and only if every element of A is in B. So this time, so every element of A is in B, and there is at least one element in B that are not in A. So in this case, we call that a proper subset. So the symbol denotes for not a proper subset. So this stands for a proper subset. So symbolically, A is a proper subset of B if and only if for all X, X is in A, also X is in B. So as you notice, almost same yung definition from the previous discussion, the subset. The only difference is in proper subset, wala na po yung equal sign. Because in the subset, you can have the same elements A and B. So let's say set A, same din ang elements ng set B, then A is a subset of B. But for the proper subset, it should be set B as at least one element. So this is very important. So at least one element. So let's have an example. A is CDE. So we have this one. A is CDE, B is ABCDE, C is AACBD, then our universal set is ABCDEFG. So as you can see, A is a subset of B because, or A is a proper subset of B. So we have CDE, we have CDE, and we have at least one element of B. So we have this one, element A, which is not found in set A. Also, we have B, which is not found in set A. Therefore, A is a proper subset of B because all elements of A is in B. And there is at least one element of B that are not in A. Let's have another example. In this case, we have, is A a subset of B? Or is A a proper subset of C? Let's take a look at this one. So in this case, A is CDE and C is EACBD. So C, then we have also D, and we have also E. So in this case, set A is also a proper subset of set C. How about B and C? Is B a proper subset of set C? So in this case, since there is no, they are the same. So set A, we have A, B, C, D, E. Set C, we have A, B, C, D, E also. And there is no at least one element that are not in C. Therefore, B is a subset of C. Hindi po siya proper subset. So it's only a subset because all the elements in B are found in C. But there's no one element, it should be at least one element in C that are not in B para masabi nating proper subset. So B is a subset of C, not a proper subset of C. Okay, so that's it. So that is the difference between a proper subset and subset. So what do we mean all by equal set? So given set A and B, A equals B if and only if every element of A is in B. So this time, every element of A is in B and every element of B is in A. So in other words, we can say that two sets are equal if and only if A is a subset of B and B is a subset of A. So you have to show both that A should be a subset of B and B should be a subset of A. Then you can conclude that A is equal to B. So that is the very important. In other words, two sets are equal. Dapat same po talaga lang yung elements nila. So let's have this example. So A is equals to set with elements A, B, C, D, E and set B with the elements A, B, D, E, C. As you notice, the set elements, we have A, B, C, D, E. All the elements of A are found also in set B. And likewise, all elements of B are also found in the elements of A. Therefore, since A is a subset of B and B likewise is also a subset of A, thus A is equal to B. So take note, this is how we prove that two sets are equal. You need to show that A is a subset of B and B is a subset of A. Take note, we're not using proper subset. It should be subset. So the last kinds of set, we have the power set. So given a set S from universe U, the power set of S denoted by this symbol is the set or is the collection or sets of all the subset of S. So given the sets, we need to get all the subsets of that given set. And that will be, if we will collect those, then that is our power set. So let's have an example. Determine the power set of, let's start with letter A. Set with elements E and F. So first thing to do is to determine all the subsets of S. So the subset of S can be written in this form. So the subset of S are, first we have the set A, we have the subset F. So we need to first identify all the singleton or the unit set. So we have the unit set E, the unit set F, and then the 2. So because A is a subset of A. And take note that empty set is always the subset of a given set. So that is why empty set is part of the subset of any set. So therefore, the power set of EF is, we have the set A, we have the set F, the set EF, and empty set. So this is how to compute the power set. Another one, for the set B, so we have 1, 2, 3. First thing first is we need to get all the singleton or the unit set of each. So we have the first 3 unit set. We have set 1, we have 1, we have 2, 3. Then after that, by 2, so we have 1, 2, we have 1, 3, and we have 2, 3. And also, the set itself is a subset. And finally, the empty set. As what I've said, it's always a subset of every set, the empty set. So therefore, the power set of set B composed of 8 elements. Okay, so that's it. So that is all about power set. So these are some of the important theorems and sets that we need to understand. So 1, a set with no elements is a subset of every set. So this theorem said that in any given sets, empty set is always a subset of every set. So if empty is a set with no elements and A is any set, then empty is always a subset of set A. So take note the notation of subset. So when you say subset, you should write it in a set form. Say for example, empty is a subset of A. Okay? That is how to write. But in writing an element, so 1 is an element of set B. So the difference in writing is you don't need to put this bracket. So 1, this one. 1 is an element of B. So this is wrong. So this is wrong. That is not the correct way on how to write. So if you're writing using an element, you just put an element of B. If you're using this bracket, that is already a symbol for subset. Okay? So that is very important in writing the sets. The difference between the subset and writing the elements. Another one theorem. For all sets A and B, if A is a subset of B, then in this case, if A is a subset of B, the power set of A is also a subset of the power set of B. And finally, this is very important theorem. So this will be the basis of our if we want to know how many elements are there on the power sets of a given set. So all you need to do is count the number of elements of the given set, then use this formula 2 raised to n. For all the integers n, if a set S has an n elements, then the power set of S has 2 raised to n elements. So in this case, in letter A, n is equals to 2. So therefore, 2 squared is equals to 4. That is why there are 4 elements of the power set A. For the power set of set B, so we have 1, 2, 3, so n equals 3. So therefore, 2 to the 3 is equals to 8. So that is why there are 8 elements on this set or on this power set B. So that is the use of our theorem. So take note that the two's theorem is very important. So don't forget always that in any given set, empty set is always the subset. Okay? Operations and sets, we have the union, intersection, complement, difference, symmetric difference, and disjoint sets. And also the ordered pairs. So for the union, so the union of set A and B denoted by this symbol is the set of all elements X in a universal such that X is in A or X is in B. So either X is in A or X is in B. So in symbol, A union B is equal to the set of all X such that X is an element of A or X is an element of B. So using the Venn diagram, so the shaded area is set A and set B are shaded. So this is an example. This is the Venn diagram for the union of sets. So for the intersection of sets, so we have the intersection of A and B is denoted by this symbol. A intersection B is the set of all elements X in the universal set such that X is in A and X is in B. So the difference is, and in the union, we have X is in A or X is in B. This time, X is in A and X also should be found in B. So the intersection A and B is set of all X such that X is in A and X is in B. So this will be the shaded part or it means, in short, those elements that common to both A and B is the intersection of A and B. For the complement of A or absolute complement of A that is denoted by A complement, or this symbol A prime, is the set of all elements X in the universal such that X is not in A. So in symbol, A complement is the set of all X in the universal set such that X is not an element of A. So those are all elements in the universal set but not found in A. And that is an A complement. So the shaded area is outside set A. So for the difference, so the difference of A and B, or the relative complement of B with respect to A is denoted by this symbol, is the set of all element X in the universal set that such that X is in A and X is not in B. So this is the symbol. So X is an element of A and X is not an element of B. So the only shaded part is this part of A. So tanggal po yung B. So the difference of A and B is also equivalent to A intersection B of complement. So later on, we will check this one in our example if we get the same answer with respect to A, the difference of A and B. So for the symmetric difference, if set A and B are two sets, their symmetric difference is the set consisting of all the elements that belong to A or B but not both. So these are just the elements of A and the elements of B. So hindi po kasama yung common. And this is what we call the symmetric difference of A and B. So in symbol, we have this one. X is an element of A union B, and X is not an element of A intersection B. So let's have this example to, on some operations on sets. So suppose we have ABC equals, set A is equals to set with ABC, set B with C, D, E, the universal set with elements A, B, C, D, E, F, and G. So we need to find the following: A union B, A intersection B, A complement, the difference of A and B, and the symmetric difference of A and B. So let's start first with finding the solution for A union B. So for A union B, so we have the set A union set B. So to answer this, we need just to combine all the elements of A and B, because those are elements that can find in A or an elements that are present in B. So all in all, we have, so this will be the shaded area, and therefore A union B is equal to A, B, C, then we have D, E. So we will just combine all the elements of A and B. So for the union of sets, or the intersection, by the way, of the sets, so you have A intersection B, we have A, B, C, and we have C, D, E, then we'll just get what is common to both A and B. So the common element is C. So therefore, this is the shaded area. So therefore, the answer is the set with an element of C. So for the difference, or the complement, by the way, of set A, so we have A complement. So we need the universal set because this will be our basis to compute for the A complement, since the definition states that these are the X is an universal set but it cannot be found on set A. So we need to cross out or cancel out those elements that we found in A. So we have A, B, C, and the remaining elements are the complement or the A complement. So cross out yung A, BC. So the remaining will be D, E, F, G. So this is now the solution for A complement. Now, we have the difference of A and B. So we have A, B, C, and we have set B, the C, D, E. So this time, the difference of A and B is the elements found in A, but not in B. So we will cross out or cancel out those elements that we found in A that we can found in B. So C is the elements that we can found, or the element that we can found in set B, which is in A. So therefore, cross out yung C, and the remaining is now the difference of A and B, which is, this will be the shaded part. So cancel po yung C, kasi part din po siya ng B. So the answer is A and B. And for the symmetric difference, we have the symmetric difference of A and B is equal to A. Symmetric difference of A and B, we have set A and set B. So in this case, the symmetric difference is just the set, those elements that are in set A and set B, but not both. So since C is an element that we can found in A and B, then we will cancel out. So the remaining elements are the symmetric difference of A and B. So the symmetric difference of A and B are A, B, C. We have A, B, C, D, and E. So cross out po yung C. So that is how to get the symmetric difference of two sets. Now, next is we need to check if the difference of A and B is equivalent to A intersection B complement. Okay, so I will show you on the whiteboard on how to compute A intersection B complement. Okay, so let's start. First, so we need to write ABC. We have to write first the set A, which is ABC. So let's have the computation or the solution to show that A, the difference of A and B is equal to A intersection B complement. So first, we need this one. So set A is equal to A, B, C. Set B is equal to the set C, D, E. While our universal set is A, B, C, D, E, F, and G. So A intersection B is equal to A, B, C intersection set B is C, D, E complement. So copy first this one. So we will first answer the complement of set B. So the complement of set B are those elements that we can found in universal set. Cancel out lang natin yung nasa set B. So set B, cancel yung C, cancel yung D, cancel yung E. So the remaining will now be the complement of set B, which is A, B, F, and G. So now we can get now the intersection of the two. So what are the common? So we have first, we have A, then we have A, and we have B, then we have also B on the other side. So therefore, A and B is the answer. And yes, it's true. So therefore, we show that A, the difference of A and B is equivalent to A intersection B complement. Two sets are called disjoint or non-intersecting if and only if they have no elements in common. So obviously, there is no elements in common, then we call that as disjoint sets. So in symbol, A and B are disjoint if their intersection is empty. In other words, there is no intersection. So A intersection B is empty. So in this case, sets A and B are disjoint. So next is the ordered pairs. So in the ordered pair AB, A is called the first component and B is called the second component. So in general, we have the ordered pair AB is not equal to BA. Because A is the first component, this one B is the first component of the other side, and they're not equal. So for example, determine whether each statement is true or false. So take note that in writing the ordered pair, we are using parentheses, not the bracket. So bracket is used in writing elements. So determine whether each statement is true or false. So 2, 5 plus 9 minus 7, comma 2 plus 3. So this statement is true. Why? Since 2 is 9 minus 7. So 2 is 9 minus 7 and 2 plus 3 is equivalent to 5. So the ordered pair is equal. How about this one? We have the set 2, 5 is not equal to set 5, 2. Is this true? This is false. Because set 2, 5 and set 5, 2 is the same. Okay, so this is false. Since these are sets and not ordered pair, take note, we are using the bracket. So 2, 5 and 5, 2, when it comes to sets, they are equal. Because same lang ang laman ng ating sets. 5 tsaka 2. So, letter C, we have 2, 5 is not equal to 5, 2. This time, this is now true. This time, this is now an ordered pair. So 2 is not equivalent to 5 and 5 is not equal to 2. These ordered pair are not equal since they do not satisfy the requirements for equality of ordered pair. So to be equal, the first component should be equal to the first component of the other equation. Okay? So that is all about ordered pairs. So when you say Cartesian product, so the Cartesian product of sets A and B, written A cross B, is equal to the set of ordered pair. So we need to introduce ordered pair because Cartesian product is one of our very important operations also. So a set of ordered pair AB such that A is an element of set A and this B is an element of set B. So it is an ordered pair of composed of A and B. So let's have set A, we have 2, 3, 5 and set B we have 7, 8. So to find the Cartesian product of this, so we need to have the ordered pair of, we have 2, 3 times 2, 7. Or 2, 3, 5 cross 7, 8. Then we have 2, 7. We have 2, 8. We have 3, 7. We have 3, 8. We have 5, 7. And we have 5, 8. So all in all, there are 6 ordered pairs for A cross B. So actually, we can determine that by, so we have 3 elements of set A and 2 elements of set B. So all in all, we have 3 times 2, which is equivalent to 6. So there are 6 possible ordered pairs. So if we have B cross A, so we get different answer. So that is 7, 8 cross 2, 3, 5. So we have 7-2, 7-3, 7-5, 8-2, 8-3, 8-5. So it is important to note that A cross B is not equal to A cross, or B cross A is not equal to A cross B. So if you have A cross A, then obviously we have 9 possible ordered pairs, because there are 3 elements for A and 3 elements also for A. And if we will get the cross product or the Cartesian product, then we'll give these answers. Okay, so that's it for the Cartesian product. So the next is the language of relations. So we're done with the language of sets. So we need to understand all of those important terms and sets, because so that we can better understand the language of relations. So what is relation? So a relation is a set of ordered pairs. So it's a connection with our previous topic. So if X and Y are elements of the sets, and if a relation exists between X and Y, then we say that X corresponds to Y, or Y depends on X, and it is represented as the ordered pair XY. So the relation is represented in this as an ordered pairs. So a relation from set A to set B is defined to be any subset of A cross B. So it is a subset of A cross B. So if R is a relation from A to B, and AB is an element of R, or the ordered pair AB is an element of R, then we say that A is related to B, and this is the notation. This means that A is related to B. So for example, so let A, we have ABC to be the set of car brands, B, the STUV be the set of countries of the car manufacturer. So then A cross B gives all possible pairings of elements A and B. Hence, the relation R from A to B is given by this. So A cross B, we have AS, AT, AU, AV, BS, BT, BU, VV, and so on. So R is consists of 4 times 4. So a total of 16 ordered pairs for our set R. So let R be a relation from set A to set B. So the domain of R is the set of the dom R defined by, so the domain of R is the set of all A element of E such that ordered pair AB is an element of our relation for some B element of B. And for the image or the range of R, it is the set of IMR defined by IMR is the set of all B such that ordered pair AB is an element of our relation for some A element of A. So to understand the difference between the domain and the image of the relation, let's have an example. So given the domain and range of the given relation, so if we have this ordered pair 1, 2, 5, 0, 0, negative 2, and negative 3, 4, so our domain R is composed of a set of elements 1, 5, 0, negative 3. So these are set of our domain, or the elements of our domain. And for our range, obviously, or the image, so these are the image. So we have 2, 0, negative 2, and 4. So that is how to determine the domain and range of our relation. So for the language of functions, so what is a function? So a function is a relation in which for each value of the first component of the ordered pairs, there is exactly one value of the second component. So very important that for the function, the first component should be there's exactly one value of the second. So that is the definition of a function. So it is a relation, but then this is the very important part. the first component of the ordered pair, there should be an exactly one value of the second component. Okay, so the set X is called the domain of the function. For each element of X and X, the corresponding element Y and Y is called the value of the function at X, or the image of X. So the range of the function is the set of all the images of the elements of the domain. So a function can map from one set to another. So these are the domain of X. We have A, B, C, and these are the range of, or what we call the images of X. So A, S, so the image of B is T, the image of C is U, the image of D is B. So S, T, U, B are the range, while the domain is the set A, B, C, D. So function is a special kind of relations that helps visualize relationships in terms of graphs and makes it easier to interpret different behavior of variables. So also functions, so these are some of the application of functions. So financial applications, economics, medicine, engineering, sciences, design machineries, others. So functions is everywhere. Actually, this topic is discussed in general mathematics in your senior high school. So we just need to tackle some of those basic concepts only. So for the example, determine whether each of the following relations is a function. So for the first relation, we have 1, 3, 2, 4, 3, 5, and 4, 6. So as you can see, this is a one-to-one. So this is one-to-one. So is this a function? Yes, this is a function. Relation A is a function because for each X values, there is only Y value. So 1, the image is 3, 2, the image is 4, 3, the image is 5, 4, the image is 6. So there is only one possible values of Y for each values of X. So therefore, it does not violate the definition. So therefore, this is a function. And for set B, we have negative 2, 7, negative 1, 3, 0, 1, 1, 5, and 2, 5. This time, this is 1 or many to 1. So this is an example of many to 1. So why many to 1? So we have 1 and 2, their image is 5. Is this a function? Yes, it is a function. Notice that in B, the last two ordered pairs have the same Y value. This does not violate the definition of a function because it should be each of the component of X should have a corresponding values of Y. So for 1, we have the corresponding values of 5. For 2, we have also the corresponding image of 5. So this is a function. Now, how about this one? 3, 0, 3, 2, 7, 4, 9, 1. So this is one to many. So one to many, an example of one to many relation. Because we have 3, 0, 3, 2. So notice that this is not a function because the first two ordered pairs have the same X value. This violates the definition of a function because there is ordered pair X, but they have their different Y values. It should be only exactly one Y values. In other words, given the relation, the shortcut to determine if the relation is a function is just check the first element. If no two elements are the same, then that is a function. So if there is the first element are the same, then that is not a function. So take note in this example, negative 2, negative 1, 0, 1, and 5. So they are exactly one. Yes. So no first element are the same. So that is a function. Another way of finding a function is using a vertical line test for a function. So a graph represents a function if and only if each vertical line test intersects the graph at a single point. So in this case, which of the following can be graphs of functions? So for letter A, so you need to put a vertical line test. If that vertical line test only intersects the graph at single point, then that is a function. So basically, this example is a function. So using the vertical line test, we only intersect one. Kahit dito po tayo, kahit saan po tayo maglinya, we intersect the graph at only one point. So therefore, this graph is a function. So this one, letter B, so this is also a function because if we try to draw a vertical line, so we can have this intersection only at one point. For letter C, so this is an example of not a function. As you notice, by having a vertical line test, there's two intersections. This is the first intersection of the graph. This is the second intersection. So this violates the rule of vertical line test. Therefore, this is not a function. Now let's have the language of binary operations. So the most widely known binary operations are those learned in elementary schools, such as addition, subtraction, multiplication, and division in various sets of numbers. Binary operation on set is a calculation involving two elements of the set to produce another element of the set. So the study of algebraic structures focuses on investigating sets associated by a single operation that satisfies certain reasonable axioms. An operation on a set generalizes structures as the integers together with a single operation of addition, or invertible 2 by 2 matrices together with a single operation of matrix multiplication. The integers under addition and 2 by 2 matrices under multiplication are examples of algebraic structures known as the group. But before that, we need to formally first define what is a binary operation. So binary operations, so let G be a set. A binary operation on G is a function that assign each ordered pair of element of G. So in symbol, we have A star B equals G for all AB element of G. So the star is now the binary operation, which is a rule for any two elements in a set G. So this rule can be addition, multiplication, subtraction, division, or a combination of those operations. Now, let's now define formally a group. So what is a group? So a group is an ordered pair G, comma, star, where G is a set and star is, we already defined earlier, star is our binary operation on G. So let's have the properties of the group. So the first one is the closure property. So if any two elements are combined using the operation, the result must be an element of the set. So if we have A star B is equals to C, element of the group, for all ABC element of G. In other words, if we will apply this binary operation, we still get the resulting is also an element of the group. So for example, say if we have, let's say, integers under multiplication. So if that 1 times 3 so is equals to 3. So 1 is an integer, 3 is an integer, and the resulting answer is also an integer. So therefore, set of integer is closed under multiplication. But take note that division is not closed, or integers is not closed under division. For example, we have 1 divided by 3, and 1 divided by 3 is 1/3, and 1/3 is not an element of integers. So therefore, Z is not closed under division. Take note also that Z is closed under addition and also under subtraction. So for the next property, we have the associative property. So we have parenthesis A star B, close parenthesis, star C is equivalent to A star B star C, close and open parenthesis, for all A, B, C element of G. So we need to satisfy this associative property if we want to determine if that is a group or the given problem is a group. Another property of the group is that the identity property. So there exists an element E such that for all A element of G, A star E is equal to A star E. So in other words, it is an identity element which, for example, in addition, so the identity element is 0. Because if we will add 0 to any number, the resulting is also that number. For example, if we have 2 plus 0, that is equivalent to 0 plus 2, the resulting answer is 2. And 2 is an element of an integer. So in that case, so in addition of integers, so 0 is the identity element. So for the inverse property, for each A element of G, there is an element or the inverse of A of G such that A star A inverse is equivalent to A inverse star A, and the resulting is what we call the identity element. So in this case, so in addition of integers, so if we have 2, so we will add negative 2 such that the resulting answer should be the identity element. So we have negative 2 plus 2, and the answer is 0. Therefore, the inverse of A or the A inverse is negative 2. So, madali lang when we are talking about addition of integers. So, in addition of integers, our identity element E is 0, while our inverse is negative A. So if A is an integer, the inverse is negative A, and this is for addition of integers. Okay, so let's have an example. Determine whether the set of all non-negative integers under addition is a group. So in this case, non-negative integers are 0, 1, 2, 3, and so on. So first, we need to apply the four properties to test the set of all non-negative integers under addition is a group. So step 1, so we need to determine if non-negative integers is closed, or the closure property. So we will choose any two positive integers. So for example, we have 8 plus 14. So 8 is a positive integers, 4 is a positive integers, and the resulting number is also a positive integer. So addition is closed. Another example, we have 5 plus 10 is equals to 15. So the sum of two numbers of the set, the result is always a number of the set. Thus, it is closed. So in other words, non-negative integers is closed under addition. Next, we need to determine or check the associative property. So we will choose any three positive integers or any three non-negative integers. So in this case, we will be using A star, B star C. Is this equal to A star B star C? So this will be the associative property. So in this case, we have 3 plus 2 plus 4 is equal to 3 plus 2 quantity plus 4, because 3 and 2 plus 4 is 6 and 3 plus 6 is 9. 3 plus 2 is 5 plus 4, and the resulting also is 9. So in this case, it satisfies the associative property. Step 3, so we need to identify the identity element. So the identity property, so we have to choose any three or any positive integer. So since this is addition, so we need to add 0 so that the resulting is also 8. If our example is 9, so we add 0, then the result is 9. 15 plus 0, and the result is 15. So in this case, it also satisfies the identity element. And the identity element E is equivalent to 0. So the identity element in addition of non-negative integer is 0. And finally, so we need to determine the inverse element. So applying the inverse property, so we will choose any integer. So we need to add any integer so that the resulting is an identity element. So for example, if we have 4, so we need to add negative 4 such that the resulting is an identity element. And if we have 10, we need to add negative 10 such that the resulting element is an identity element. So take note that the inverse property or the inverse element of under addition of non-negative integer is negative A. Why? Because 4, the inverse is negative 4. 10, the inverse is negative 10. So thus, it also satisfies the inverse property. So basically, all the 4 properties of a group are satisfied. So therefore, the set of all non-negative integers under addition is a group, since it satisfies the 4 properties. Okay, so that's it. Thank you. for watching.